Okay, recording. Okay. I'm very happy today to welcome Professor Michael Gelfond to give this talk that is being done here for, to celebrate World Logic Day, which is what UNESCO has declared today is. So happy World Logic Day to everyone. Professor Michael Gelfond, he's a professor emeritus in the Department of Computer Science at Texas Tech University in USA. So he got his master's degree in mathematics from St. Petersburg University, Russia, and his PhD in mathematical logic from the Institute of Mathematics of the Academy of Sciences, again in St. Petersburg. This was in the early 70s, 1974. Then in his early work, he looked at relationships between classical and constructive logics. He has briefly worked as a software engineer, and from the 80s, almost for 4 decades now, he has been interested in understanding the relationship between logic and computer science. So he's an excellent person to give us this lesson today. He has contributed, of course, as many of you know, to the development of stable model or answer set semantics for logic programming and the answer set programming paradigm, which again, I noticed many people in this audience we use, right? And we build on. Which is founded, of course, on the stable model semantics. He's also contributed to the theories of actions and change and methods for combining logical and probabilistic reasoning, right? He's a fellow of the AAAI, and he has the honor of being awarded 3 Test of Time Awards for most influential papers by the IALP, International Association of Logic Programming. And I should also say that I have personally benefited through my interactions with Michael. It's been a nice experience working with him since the time I was at Texas Tech. So I'm very happy he agreed to give the talk today. And so now I'm going to hand it over to Michael. And I'm going to say that if there are any sort of clarification questions, you can sort of bring them up by, say, using the raise hand function in the Zoom or by typing out in the chat. If it's general discussion questions, please hold them till the end of the talk. We have time, and then we can have time for discussion questions. So, Michael, up to you now. Go ahead.
Okay, thank you very much for the introduction. Very happy to be here. You already told a little bit about myself. I was going to really start with describing my interests very briefly, because that's where my perspective comes from. So during the last 40 years of my scientific life, I was mostly interested in 2 things: achieving better understanding of the human mind and structure of the universe by discovery, refinement, and formalization of the basic categories of our language and thought. The second thing, developing a good methodology for the design and implementation of elaboration tolerant software. So the first desire led me to the traditional activity of a logician. I started with working in the area of constructive logic, which is concerned with nature of mathematical objects and their existence, and later moved to trying to better understand things like rational beliefs, causality, etc. For me, this activity, at least in the beginning, did not require any justification. Pure joy of replacing chaos by order and clarity was enough. A little later, I understood that impact of logician's activity may be much broader and more consequential. I want to quote Leibniz, who viewed this activity as second in importance only to the activities of prophets and kings. So that's where I'm going to start the story of logic and my relation with it in computer science. Every one of you probably heard about universal symbolism or universal characteristics, which was introduced by Leibniz in the 17th century. Here is a quote. Universal symbolism is a universal notation by use of which any item of information, whatever, can be recorded in a natural and systematic way. And second, the means for manipulating the knowledge thus recorded in a computational fashion, so as to reveal its logical interrelations and consequences. 2 more quotes. A man who is neither a prophet nor a prince can ever undertake anything of greater good to mankind and more fitting for divine glory. And the second, mankind is still not mature enough to lay claim to the advantages which this method could provide. Among these advantages, Leibniz mentions better understanding of nature and man, great scientific progress, and even end to religious strife and wars, achieved by reducing disputes to computation. Well, we still have no universal symbolism, and not yet learned to gracefully use parts of the symbolism which have already been developed. So he was definitely right in his second quotation. I happen to agree with the first one. I believe it's a very, very noble activity. Even though we don't have this universal symbolism, logicians interested in good of mankind and or divine glory continue striding toward the goal. Perhaps eventually we'll mature enough to fully develop and use the method. So in this talk, I'll discuss several steps in this development, some big and some small, which I believe worth remembering and thinking about. The first one, as expected, probably George Boole. Important step toward Leibniz's goal was made by Boole, who believed that a successful attempt to express logical propositions by symbols, the laws of whose combination should be founded upon the laws of the mental processes which they represent, would be a step toward a philosophical language. This philosophical language is the same as universal characteristic. In his An Investigation of the Laws of Thought, Boole did exactly that. He describes certain type of reasoning and reduced it to Boolean algebra. And as all of you know, it is now one of the foundations of our information age. Second step I would like to mention is axiomatization of mathematics. In the first half of the 20th century, ideas of Boole and much earlier ideas of Euclid led to expanding Boolean logic by quantifiers, new laws of inference rules, and so on. Also, a small number of axioms of set theory were found, capable of representing almost all mathematical theorems. Unfortunately, almost is inevitable, as was shown by Gödel, but it still was a very impressive achievement. Alfred Tarski started the problem of expanding axiomatic method from mathematics to other sciences. The program further developed by McCarthy and others so far proved to be most successful in computer science, where it led to the development of declarative programming paradigm and logic-based approach to AI, to mention only two things. So first I'm going to talk about declarative programming. What is it? I define it as an attempt to apply axiomatic methods of mathematics to computer science and to practice of programming. It is obviously very closely related to my second scientific interest, development of methodology. So it does suggest design of methodology, according to which knowledge relevant to a given class of computational problems is represented by a theory in some precise mathematical language. A particular computational problem is reduced to computing consequences or computing models of this theory, and general reasoning algorithms are used to compute these consequences or models. That's a basic idea of declarative programming. So clearly, representation of knowledge requires formal languages. And it's important that languages are not just means for communication, they means for thinking about computational problems as well as for communicating information about them. They often divide into algorithmic and declarative. Declarative describe properties of objects an agent can use to form rational beliefs, reason, and act toward achieving the desired goal. You all know about algorithmic languages. So let's look at some simple examples. It's a family example which can be found in any book. Given a database containing entries for three people, John, Mary, and their son Sam. John is the father of Sam, Mary is the mother of Sam. Problem. Teach the database a new family relation parent and check if the term is understood by this problem. So how can we do that? So the following two statements can be viewed as a definition of relation parent written in a declarative language called Datalog. You can also use Prolog or NCSP. Datalog is probably the simplest language in which it can be expressed. So X is a parent of Y, if X is the father of Y, or X is the mother of Y. Used together with a database, father John and Sam, mother Mary Sam, it's supposed to represent whatever knowledge we have about parent and particular people. So now you have to make sure that the program understood the notion of parent, how to do it. You're going to test it by asking a number of questions to be answered by an inference engine of Datalog. If the answers are satisfactory, the program learned. This may sound non-scientific, but it is exactly the method we use to check human understanding. So here's the first question. Is John a parent of Sam? Let's see if this works. Oh yeah, it does. So we represent it, and the answer is yes. Who are Sam's parents? We use variable, write an equation, find X such that X is a parent of Sam, and get to answer X is John and X is Mary. So probably everyone's seen this program. So why is solution to our original problem is interesting? And I believe it's worth seriously thinking about it. So my most important answer is that thanks to our language, Datalog in this case, the thought process which led to this solution is very different from that used in traditional programming. Language's main purpose is to help us to think. And it successfully done that, in my judgment. Moreover, the solution is short and easy to understand. Mathematical definition of parents is very close to the informal definition. No knowledge of data structures and search algorithms is required. And finally, the program has a high degree of elaboration tolerance. In this case, it just means it's not difficult to expand. So let's try to expand. First, we introduce a new notion of ancestor. And it is done by recursive definition. Most of you probably seen it. Second, I define a notion of number of children. And to define number of children, I'm using set notation and count the function on set. So this function takes this set as an input. It just counts the number of elements in this set, which means counts the number of children of P. And the number of the children is n, then n is the number of children of P. So it's a very simple notion if you understand the notation. By the way, such functions on sets are called aggregates. So it's an easy expansion. Let's discuss it a little bit again. First of all, we've seen recursive definitions. Remember, I said that my goal was to better understand some basic categories of a language. So recursion and recursive definition is certainly one of basic categories of our language, and actually of our thought too. The semantics of Datalog, given in terms of minimal Herman model of a program, provides an accurate account of this category. Datalog also allows aggregates, so it can count, sum, and so on. But it prohibits certain definitions. It prohibits definitions which use recursion through aggregates. Our program has no such definition, so it has precise semantics. It exhibits expected behavior and can even be proven correct if you define what what ancestors mean without using the program itself. But interestingly, we still have no universally accepted semantics for recursive aggregates. There's a number of competing approaches which may disagree on questions like what should be the models of programs Let's look at these two problems. Oops. I just was able to do it a moment ago, and now I can't. Okay, probably now I can. So this is a number of elements in the set X which satisfy P. And if the number of elements is greater than or equal to 0, then P of 1 is true. So the number of elements in this set is greater than or equal to 0, then P of 1. The second says more or less the same thing. If Y is the number of elements in this set and Y is greater than or equal to 0, then 1 satisfies P. So is it possible for one of these programs to be consistent and another inconsistent? Should they both be inconsistent? Should they both be consistent? To answer this type of questions, we need better understanding of self-reference, methodology of language design, and we still don't know the answer. We don't even know exactly how to argue about which answers are correct. And we don't even know it makes sense to say that a particular answer is correct. So all of this requires a lot of thought. Now a few more things to know about Datalog. Datalog programs are easier to develop, maintain, and modify than traditional DBMSs. For recursive queries, they outperform such systems by orders of magnitude, which surprised me greatly. Datalog inference engines often use traditional SQL techniques to get efficient access to huge collections of data. Originally, Datalog could only deal with small sets of data. Extensions of Datalog, like answer set prolog, allow reasoning with incomplete information. Multiple applications of Datalog include data integration, information extraction, networking, etc. Now, we talked about my first example. Next, declarative programming in knowledge representation in AI. I want to talk about two classical AI problems: formalization of reasoning with defaults and formalization of reasoning about actions and their effects. Both problems are crucial for formalizing common sense reasoning and for the development of methodology for the design of intelligent agents capable of acting in a changing environment. Of course, they're not only of interest from the standpoint of methodology, of design, but also if you want to really understand these basic blocks of our thought and language. So in everyday reasoning, we often use defaults, statements of the form, normally elements of class C have property P. It seems that a substantial part of our education consists of learning various defaults and methods of reasoning with defaults and their exceptions. The problem of understanding and formalizing default reasoning remained unsolved for decades. It is mostly solved now, which in my judgment is a great achievement of many people. So here's an example of default reasoning. Again, start with a database. Bob is a parent of Mary and John is a parent of Sam. And let's look at the default. Parents normally love their children. One expects answer to queries: does John love Sam? Does Bob love Mary? To be yes. You will later learn that John is an exception to this rule. He hates his son. And our previous conclusion that John loves Sam will be withdrawn. A consequence relation which allows a reasoner to withdraw previous conclusions given new information is called non-monotonic. Non-monotonic consequence does not appear in mathematics and hence has not been studied in classical mathematical logic. So, problem: develop new logics with non-monotonic consequence relations. First such logics appeared around 1980. Answer set prolog is probably most popular such logic to date. at least one of most popular. According to Stanford's Encyclopedia of Philosophy, the emergence of non-monotonic logics is one of the most significant developments both in logic and artificial intelligence. So again, this notion of non-monotonicity and the corresponding logics is truly a great achievement. I actually don't need encyclopedias of philosophy to see that, but I'd like to have some support of authority. So defaults and default negation in ASP. Let's show how defaults can be represented in ASP. First, let us look at this line here. What it says is x loves y if x is a parent of y. So the interesting part is this, which it says is normal. To understand this, we need to know this symbol. This is classical or strong or explicit negation, and is read as P is false. And TP is a default negation or negation is failure, and read as there's no reason to believe that P is true. The rule itself is read as follows. If x is a parent of y and there's no reason to believe that he does not love y, then he does. So this is a typical representation of a default in ASP and similar in other languages. Let's see how it works. We have the default, and we have this fact, and it entails properly, according to the semantic of ASP, that John loves Sam. But addition of a new fact, which says John doesn't love Sam, forces the program to replace its conclusion by John doesn't love Sam. Previous conclusion is withdrawn. Exactly what we want. This is not a more general solution. It takes care of so-called direct and strong and weak exceptions to defaults. There are also indirect exceptions. I'm going to give an example in a moment. And to represent such indirect exceptions, I'm going to demonstrate how it is done in an extension of ASP, which uses so-called consistency restoring rules. The rule says, if the reason associated with a program believes the body of the rule, then it may possibly believe its head is true. However, this possibility may be used only. There is no way to obtain a consistent set of beliefs by using only regular rules of the program. So it's kind of an emergency rule. Here's an example. Okay. The first rule is a default, which says elements of class C satisfy property P normally. The next one says Q of X is P of X, and we have a fact that A belongs to the class C. This entails P of A and Q of A. Default works. But suppose now we learned that Q of A is false. In our previous example, we learned that P of A is false. Here, it's not a direct consequence of the default, it's an indirect consequence of the default. In standard ASP, the program becomes inconsistent. But if we add to our default this consistency restoring rule, which says afterwards some elements of class X may not satisfy P, but that's very rare. Don't really use it unless you have to. Then we're going to get the answer we want. Withdraw previous conclusion and conclude that Q of A is false. So the example shows how a long-standing problem in knowledge representation found a simple solution via the development of logical languages containing new non-monotonic language constructs, such as default negation and CR rules. There are, of course, some other solutions to the same problem, also good. Currently, we have powerful languages with non-monotonic inference, reasonably efficient reasoning systems, and non-trivial mathematical theory. In my judgment, the next almost unexplored step is the axiomatization of large parts of common sense knowledge. Next topic, representing effects of actions. Well, let's look at the story. Initially, John was in the corridor holding a book. Then he stepped in the office. To reason about this story, we need to axiomatize effects of action. P moves into location L. The initial state is 0 of the domain described in this story. Can be described as follows. First of all, we're going to need time steps. Since I'm talking about initially, my time step here will be 0. And it says John is in the corridor at time step 0. And book is in the corridor at time step 0. Which is not needed actually. Something is wrong here, but it doesn't matter. John is holding the book at time step 0 and so on. The axiomatization we are looking for, used together with the initial state, should be able to conclude that after the move at step 1, John is in the office, book is in the office, John is still holding the book. To achieve this, we are going to formalize direct and indirect effects of move and the inertia axiom which says things normally remain as they are. Direct effects are represented as follows. If this action, P moves into L, occurs at time t, then at the next time step, P will be in L. That's comparatively easy. So the question is how to represent indirect effects of actions. It was a long-standing problem, and here's a simple solution. You just describe relationship between these relations, in, hold, and so on, at one step t. So let's see what it says. If at step t, P is in L, and P is holding O, then at the same time step, O is also in L. Similarly, second example. The axioms elegantly describe changes the action causes in the domain, but say nothing about things which remain unchanged. So if we know that John moved to the office at time step 0, we will be able to conclude that he will be in the office at time step 1, but we will not be able to conclude that he is still holding a book. He used to be holding it at 0, but is he going to hold it at 1? And without proving this, we will not be able to prove that the book is also in the office. So we need to describe what is unchanged. And the challenge of finding second representation of what does not change constitutes a famous frame problem. And the solution is suggested using inertia axiom of Leibniz. Things tend to stay as they are. The axiom is a default, and at the time no one knew how to represent the defaults. Now we do. And here's a standard representation of this default in the way I described. So as expected, the resulting program derives whatever it is you wanted to derive. This description forms a basic part of programs, which find plans for achieving the agent's goal, explanations for unexpected events, etc. And the methodology I briefly described by this example is now used in the robotics decision support system, question answering system, and so on. Development of ASP-based logics, capable of representing and reasoning with recursive definitions, aggregates, defaults, effects of actions, etc., was going hand in hand with discovery, optimization, and implementation of powerful reasoning algorithms. This led to the emergence of remarkably efficient reasoning systems, which made ASP a practical tool of declarative programming. This is not the focus of my talk, but for illustrative purposes, in the next few slides, I will briefly comment on one such application. It is a story by Gerhard Friedrich. I'm just repeating it. He is a former head of the Department of Configurations and Diagnosis at Siemens, Germany. He and his pretty large group worked on a configuration problem for more than 20 years. They use different methods, including procedural programming, constraint programming, etc. The configuration problem is difficult. For instance, in telecommunication domain, just focusing on hardware, there are 30,000 modules of 200 types, 1,000 frames of 50 types, and so on. Recent use of ASP allowed reduction of initial development cost by 66%, reduction of early maintenance cost by 80%, productivity increased by 300, enhanced user interactions, explanations, incremental configuration, repair, and so on. In this case, Set Prolog delivered and Set Programming delivered on its promise. Friedrich gave an example of ASP program consisting of 12 rules. Quote, by this simple ASP program, we solved real-world instances which could not be solved by the in-house tool. In his estimate, ASP is a historical leap for AI. On one hand, I agree with him. On another, in my judgment, we are still very far from realizing the ASP potential for industrial applications. But I'm moving in the right direction. We need to further improve efficiency of algorithms and implementations for ASP and its extensions. And most importantly, we need to teach logic. Until we have people who are at least a little bit familiar with logic, it will be difficult to advocate these methods. I don't believe we will be ready for its advantages, as Leibniz warned us about. So next topic, understanding uncertainty. One of the most important tools for understanding uncertainty is the theory of probability. This was the focus of a probabilistic approach to AI, which developed powerful knowledge representation tools and reasoning methods, utilizing graphs and Bayesian reasoning. In this approach, probability of a proposition A is understood as a degree of agent belief that A is true. Here's an example of graphical representation of probability. The famous example is an example of a Bayesian network, actually a causal Bayesian network. It describes the relationship between rain, sprinkler, and wet grass, this directed graph, and in these tables, it gives probabilities and conditional probabilities of this event. Here, the probability of rain, probability of sprinkler being on, given rain, and so on. This is a remarkable way to succinctly describe probabilistic models. Probabilistic model normally consists of probabilistic possible worlds, probability measures of these worlds, and probability function defined on sets of such worlds. So possible worlds, assignment of values to variables, probability measure is given by tables, and probability function is standard way defined via probability measures. Work on causal Bayesian networks clarify the relationship between probability and causality, and led to great achievements in AI, statistics, and other areas dealing with decision making. There are several remarkable books by Judea Pearl and others who describe this. For a long time, logical and probabilistic approaches to AI developed independently, but now there is a substantial amount of interaction. I strongly believe that we actually have one single paradigm combining both logical and probabilistic reasoning. This view is supported and probably goes back to Boole. Common foundations are evident from the full title of Boole's book, An Investigation of the Laws of Thought, on which are founded mathematical theories of logic and probabilities. He also viewed probability of an event as a degree of belief that this event has taken place or that it will take place. So according to him, reasoning about probability is simply reasoning about degrees of belief. So how can we put logic and probability under one roof? First, recall that in the original interpretation of ASP, the program's model does not represent possible state of the world, but rather possible state of agent's beliefs. Hence, Set Prolog has 3 degrees of belief. If P belongs to M, to the model, the agent believes that P is true. If not P belongs to M, the agent believes that P is false. Otherwise, an agent neither believes nor disbelieves P. He just doesn't know. So P-log is a knowledge representation language, which is an extension of ASP for reasoning with probabilistic knowledge. It allows arbitrary degrees of belief, arbitrary real number from 0 to 1. Here's an example of a program written in P-log. It's a famous so-called Monty Hall problem. I was told that Monty Hall was a television host, and he played a game with a volunteer. So there are 2 actors here in Monty Hall and a player. And there are 3 doors, and behind one of these doors is a prize. And the player thinks about it and selects one of the doors. After selection is made, Monty is obligated to open one of the remaining doors, which does not contain the prize. The player can switch his selection to the other unopened door or stay with his original choice. So the question is, does it matter if he switches? The correct answer is yes. However, the lady who published the solution received thousands of letters from her readers, the vast majority of which, many with PhD in math, disagreed with her answer. So it may seem strange at the first glance, but the phenomenon was clearly recognized by Boole, who wrote, I think it to be one of the peculiar difficulties of the theory of probabilities, that its difficulties sometimes are not simple. The solution of a problem may appear to be conducted according to the principles of the theory as usually stated. It may lead to a result susceptible of verification in particular instances, and yet it may be an erroneous solution. I strongly believe that one possible way to alleviate this difficulty is to define probability with respect to explicitly stated knowledge base of the reasoner. It is, of course, not done in classical probability theory, but it's quite natural for those who do logic and knowledge representation, or at least should be. Here is a P-log program. P-log, unlike ASP, is a sorted language. So we have first declarations of sorts. We have 3 doors. We have Boolean variable, we have variable selected price and open, which range over doors. So selected equals D means selected equals 1 means door 1 was selected. And you have a can open, functions from doors to Boolean, and can open D means door D can be open. So here are the rules. The first one is the default, which says normally every door can be opened. And the next rules are exceptions to this rule. If door is selected, it cannot be opened. If price is behind the door, this door cannot be opened. Huh? Are there questions? Makan?
That I can see. I think somebody just left their mic open. Please continue.
So here's a probabilistic part of a program. Values of variables, price and selected, are chosen at random from the set of all doors. This is written as follows. Value of open is chosen at random from a set of doors which can be opened according to the rules of the game. So that's how it is written. Open can
Just a minute, Michael, I can't hear you. Okay, try
and you
again.
hear me now?
Yeah, now it's good. For some reason, you got muted. Just a second. Yeah, go on now. Sorry.
I swear I didn't touch anything.
No, that's okay. It happens. Yeah.
So here I'm describing how to read this statement. It says the value of open will be selected at random from the set of four doors which can be opened. So that's a whole program in Prolog. It's short and very close to English story. So a little bit more about this random construct. According to the semantics of Prolog, random price can be replaced by rule price is 1 or price is 2 or price is 3. And the second rule can be replaced by a similar rule for open plus constraint which says it's impossible to open door X which cannot be opened. This translation is not entirely accurate but almost accurate. Larry selects the first door. This can be stated as follows. So the new program now defines the following possible rules. Let's look at them closely. Still have time. Select didn't fit, so I just have cell equals 1 everywhere in every possible words because that's what he did. Price can be behind door 1, 2, or 3. If price is behind door 1, what doors can be opened? Because 1 is selected and price is behind 1, 2 doors are available, door 2 and door 3 in both cases. So there are 2 choices to open a door. In this possible world, 2 is opened. In this one, 3 is opened. Let's look at W4. Price is behind 3. 1 is selected. Only 1 door can be opened. There's no choice. It is just open. How can we assign probabilistic measures to this? Let's look at this. There are 2 random variables, price and open. When the value of price is selected, it's selected on 3 values, 1, 2, 3. We assume all of them to be equally likely, so probability of price to be 1 is 1/3. What about open? Open has 2 possible values, 2 and 3. So probability or probabilistic measure of this open bin 2 is 1/2. Therefore, probabilistic measure of W1 is 1/3 times 1/2, 1/6. If you do similar computation for W4, you're going to get 1/3. It's because open here doesn't really have any choice. You must select 2. So suppose now Monty opened door 2 and the player recorded observations. that door 2 is open, and there is no prize behind 2. Updated program has two possible vaults, W1 and W2. And it's easy to see that W4 is twice as likely as W1, so changing the door doubles players' chances to win. So I have to say that writing this program really helped me to understand why the answer given by this lady who published it is correct. I kind of understood it before, but I understood it much better when I was able to explicitly state the rules of the game in formal language and analyze these rules precisely. So rules of the game written in Prolog are close to the informal descriptions. There was no difficulty in writing these rules. In fact, solution to the problem consists in simply stating these rules. The rest is automatic. Notice that if this rule were removed from the program, and it wouldn't make any sense to change the door. And I believe that's what happened with many people. I looked at actual descriptions of this problem, and sometimes they're written in a way which doesn't tell me exactly is it possible to open a selected door or not. So syntax and semantic of Prolog itself is close to that of ASP. Possible vaults of the program are answer sets of its ASP translation. Probabilistic measure is defined in a natural way using the indifference principle, which says possible outcomes of a random experiment are assumed to be equally probable. You have no reason to prefer one of them to any other. That's what we used in our reasoning here. There's another statement, type of statement in Prolog, causal probability statement. So the form of this, it says the causal probability of A given B is whatever it is, B. And these statements are used for computing probabilistic measures. So here's an example. I'm going to go over it briefly. Program pi below represents knowledge about whether a certain rat will eat arsenic today and whether it will die today. Arsenic and death are random Boolean variables, and these statements give us probabilities. Probability of rat consuming arsenic is 0.4. Probability of death after consuming arsenic is 0.8, and so on. But there's also this index C here, which indicates causal relationship, causal dependency. It is used in a program, its use in a program expresses the fact that the rat's consumption of arsenic carries information about the cause of its death. So it's kind of similar to directed arcs in causal Bayesian net. Okay, so that's the whole program. The program demonstrates the difference between observations and deliberate actions. It entails that, as expected, probability of arsenic is 0.1. Probability of arsenic after death is observed is this. And probability of arsenic if rat is killed, say, with a gun, unchanged. So observation of death increases our belief that the rat had eaten arsenic. But deliberately killing does not. As pointed out by Pearl, the difference between conditional observations and on deliberate actions is very important in decision-making and other types of causal reasoning, and actually helped me tremendously to understand probability. I was kind of confused about it, but couldn't figure out what the problem is. And Pearl kind of, in his book, explained it to me. I guess I'm going to jump over this. And I'm going to jump over this. Should I? No, probably not. It is worth noting that conditional probability, A, probability of A given B, where probability function is defined by program P, can be simply defined as probability of just A with respect to a different knowledge base, which consists of pi plus whatever it is you conditioned. So in some respects, it is more general than the usual one. You can condition on defaults, rules introducing new terms, deliberate actions in the sense of Pearl, etc., which is not possible in classical probability theory. While conditioning observations only eliminates possible worlds of the program, it is not necessarily the case in general. So to see it, consider the following problem. It's just a default. It says normally, I'm sorry, it's not a default, it says A if there's no reason to believe B. And the second rule says if B then A is random. Since this rule is not activated, the program just has possible world A, and hence probability of A defined by this program is 1. Let's expand the program by B. Add B to it. That's what it is written. Now clearly the first rule is cancelled. The second rule is activated. A is random. There are two possibilities, is true, is false. So in new program, probability of A is 0.5. So something, it's very simple, but also very strange for people who work in probability theory, because addition of new information changed our probabilistic model. Changes are not normally described in any formalism. You have your model, you do computation, situation changes, you drop your model, and you start working again. It's not the case here, it's all done under one umbrella. Now I would like to say something about things I don't really fully understand since I didn't work. Well, I can say fully understand. I don't understand as well as previous things since I didn't really work in this area. So far we assumed that knowledge needed to design an agent can be extracted from experts and obtained by introspection. Obviously, this is not always the case. You may need to extract relationship between variables from a large collection of unstructured data. There are many approaches to developing learning algorithms which address this task. The idea is to set up basic parameters about the data and train the program to learn on its own by recognizing patterns. Important recent advances in learning algorithms are based on the notion of neural network. This notion is pretty old. It goes back to Frank Rosenblatt in '58 and probably even earlier to McCulloch and Pitts. So Rosenblatt introduced two layers neural network, which defined a particular type of functions. It was quickly shown that such networks cannot predict the output of XOR logic gates, and this discovery slowed down research in this area dramatically. It was later realized that the use of additional layers allow networks to represent a very large class of functions. As I realized because the corresponding mathematical theorems we actually already know. Well, I couldn't stop myself from showing the network since I spent a lot of time long ago making a picture. Now, there are nice algorithms which, given parameters x and y, and the training data from a large data set D, learn a neural network N, which approximates the relationship between X and Y in D. So it's a typical approximation problem. The new thing is that approximation function is represented by a neural network. So it's still a question of knowledge representation, but this time we are representing the function. For a long time, these algorithms, however, were too slow. In the last decade, the efficiency of reasoning with neural network increased dramatically. This, together with availability of huge amount of data, led to the development of the field of deep learning with its remarkable application. There's a lot of hype about it, but also a lot of real applications. So, is logic in any way related to deep learning? Well, it is beginning to be used to speed up learning algorithms and explain their results. The basic idea is really simple. Let's apply the algorithm, learning algorithm, with knowledge base T, describing known dependencies between X and Y, and use these dependencies during the learning process. So what you used to have training data from a big data set. Now, in addition, you have this theory T. And in learning, approximation of whatever function you have in big data set D, you now use these dependencies. The trick, of course, is exactly how to do it algorithmically. A number of recent results show that this method substantially increases efficiency of learning, neural net N, which approximates the relationship between X and Y and D. On one hand, it was kind of almost obvious that it's supposed to do so. But it's always nice to have some confirmations. And we do have some confirmations now. Moreover, the net N we just constructed can be used to discover a new set of dependencies, R, such that neural network built using knowledge-based T union R instead of just T defines essentially the same function as N. These newly discovered properties of data can help to explain the algorithm's results. It would be interesting to see accurate formulations and proofs of correctness for this type of algorithms. As I said, I'm not an expert on it, but I kind of looked and I couldn't find it. It is also interesting to investigate if deep learning can help to learn common sense axioms, which are currently discovered by introspection. And there are many other interesting questions. This type of work is new, and more insights will be needed before we really understand the picture. Now, I talked for about an hour. Time for conclusions, I was told. So, one goal of this talk was to bring to my mind and to the minds of my listeners clear awareness of a continuous line of thought aimed at eventual realization of Leibniz's dream. It's an awkward phrase, but I couldn't come up with a better one. A thought, however, I believe is important. What happened when I talk to students and young researchers very often about their field of research, logic, knowledge representation, computer science, and whatever, I often ask what they believe to be most important achievements in their area. And sometimes I get some answers, but very seldom. Most people just don't know and don't remember. And they don't have this tremendously important feeling of a communication between generations. And this is not just about you and me. This is a long project, very serious one. And it's important to know that. Of course, it's difficult to convey in talks, but it's worth trying. So the progress always looks slower than we want. But in reality, our understanding increases at a fast rate. So to those of you who are interested in making Leibniz's dream come true, my advice is the same as was given to British citizens before the Second World War. Keep calm and carry on. I learned it very recently and I liked it. Remember that your work is second only to that of prophets and kings. And since no true prophets and kings are currently left in the world, it is second to none. Now I'd like to finish by mentioning some problems to solve briefly, and then I answer your questions if you have any. So the first one, which interests me most right now, the first two actually interests me most, I'd like to develop better understanding of causality. I'd like to put causality under the same umbrella as probability, defaults, recursive definitions, and so on, and logic in general. There's substantial work toward it, substantial effort to do that, but we are still far from fully understanding the topic. Next question, figure out how large amount of knowledge can be organized to allow an agent effectively identify and access its parts relevant to the agent's goal. According to philosophers, it is actually part of a frame problem. So how to organize our knowledge so we can get easily access to a frame of reference we are dealing with in a particular situation. And again, there's work in this direction, but much more needs to be done. Next, axiomatize and combine together various pieces of common sense knowledge. Concentrate on some basic notions such as crossing the boundary, exchange, refinement, rights and obligations, etc. The list is pretty long. Next, better understand traditional topics of logic, such as the relationship between knowledge and belief. I'd like to be able to say something like, if you believe that P is true but don't know, if you believe that P is true but don't know it, then do something. Understand the relationship between beliefs and actions, how our beliefs determine our actions. Understand the nature of counterfactuals, and bring all of that to the realm of declarative programming. Philosophers work on it and they made a very substantial progress. But to bring it closer to declarative programming is non-trivial and important. Study logical theory together with a set of operations defined on it. This is supposed to be similar to the move from data structures to absolute data types. Instead of thinking about how to represent a set, we are thinking about how to represent a set with a collection of operations. And representations are different for different operations. I believe our knowledge representation can learn from this. Sometimes our representations will be different depending on operations. Next, study behavior of logical systems in the context of agent architecture. So what happens with an agent? Agent observes, selects a goal, makes a plan, acts, repeats the story. Okay? So here, you not only reason about planning, for instance, or explaining observations, you also update your knowledge, more or less constantly. And we know how to add knowledge, but we don't know how to remove knowledge well enough. And here, we not just have a stationary system, system changes. So our reasoning should adjust to these changes. So people working on multi-short ASP, trying to do something like this, quite often very successfully, I'm told, but we need to do much more. Recently, I've heard a talk by Bob Kowalski, And my interpretation of what he said, don't hold him responsible, is something like this. This inertia axiom, which we use to describe what doesn't change, is a remarkable tool if our time span is not too long. If time span is long, then we have to do a lot of reasoning, which is unnecessary, and it slows down our reasoning. So how can we develop algorithms which shorten this time span, knows what to cut and how to restore what was cut if necessary? As far as I understand, I don't have the slightest idea how to do it. Next question. Figure out when our theory can be viewed as a refinement of another theory. Very often what we do, we take a theory and we refine it and refine it and refine it, and we reason on different levels of refinement. There's some work in this direction, but not much is known yet. There's a large number of other questions, but I'd like to stop and attempt to answer yours if you have any. Thank you very much again, and thank you, Mahan, for the invitation.
Thank you. At least my mic is off, so I can clap. Okay, so now we are ready, or we are opening up this for questions. So does anyone have any questions? I mean, I guess I'll still keep the, let me know in the chat or by raising your hand and I'll call on you in some sequence. Any questions, anyone? Okay, Paul has a question and then Aaron has a Paul. You go first, Paul Levy.
Hi. At one point, you said that the possible, what to say, degrees of belief were either you believe it's true or you believe that it's false, or you don't have a belief either way. And then you said that in Plog, it's generalized so that you have degrees of belief going from 0 to 1. So you said it was extended. You said it was extended. If you could go back to that slide.
I'm trying.
And I didn't understand how that was an extension. How that was an extension of the 3-option version. I mean, is it like you got beliefs going from 0 to 1, but also another degree for like total ignorance, or is total ignorance a half, or what?
Let me find it, just give a second. Okay, probably here.
This is it, yeah.
In what sense it is an extension? Well, suppose you don't have randomness at all. So you just have a program of Plog without random statement in it. Then this is just a program of ASP. Okay?
Mm.
So in one sense in which it is an extension. So the question is, suppose you have your model and you have neither P nor not P in it.
Right.
Uh,
Do you represent that as belief value of a half?
that's what I'm trying to think how to answer. No. Let me try to explain why I'm kind of reluctant to immediately answer this question. Because it's not entirely clear what it means that he neither believes nor disbelieves P. It's also possible that he doesn't know P. He's not aware of it at all. So there could be some difference. Is P defined on this value or not? If P is defined on this value, it will be 1/2. If P is not defined on this value, the probability is just not defined. And I can try to come back to you and answer it in the form you send me an email.
Okay.
Paul, can I move to the next person or do you want to? Okay, so in that case, I go to Aaron next and then Vladimir.
Thank you very much. I'm sorry I missed the beginning, and that you may have said something about my question then. I was at another meeting, so I was late. Excuse me. The end of your talk was very general, and this is a question about how general you intend it to be. I've always been fascinated by the discoveries of the ancient mathematicians, hundreds of years before Euclid, who made fantastic discoveries, including, for example, many ways of proving Pythagoras' theorem long before Pythagoras was born. You know about that kind of thing, I see from your nodding. And I wondered whether you think those modes of geometric reasoning are covered in what you were talking about today. They didn't seem to me to be, but that I was wondering if that's just my lack of understanding of what you were saying.
No, I absolutely agree with you about tensions. They are not covered. It's a very small portion of what I could possibly say on the subject.
Okay.
Wasn't intended in any way to be even close to full description.
Right.
And it's
I also, simply because I think very few people are interested in that.
Well, a couple of times in my life, I taught history for computer scientists. And I normally start with Pythagoras' theorem. I kind of like this subject.
Right. Okay, thanks.
Vladimir, you're up next.
Michael, thank you for the interesting and inspiring talk. You mentioned that George Boole viewed probability as degree of belief. And there's also a very different view of probability as a frequency when an event happens many times. And it seems that these are two different ideas that lead to the same, almost the same mathematical theory. So can you comment on that?
Yeah, I can try. So when I was describing what I wanted to do, I said discovery, refinement, and formalization. So people discovered this idea of probability. And when they started to refine it, they came up with two rather different interpretations, frequency and belief. And there's a remarkable and mysterious thing happened. And in many cases, the same mathematic works for both interpretations. But it is not always the case. And it caused, to me at least, a tremendous amount of confusion. When I studied probability, as you know, I studied it as a particular subject in measure theory. Okay? It was beautiful, perfect, very nice. Then you move to statistics and you try to figure out how can I possibly use this frequency theory to decide what I can do in this particular unique case. And so statistics didn't make much sense to me until actually I read Pearl. So even though I believe you are right in many, many cases, the same mathematic works, there are cases where it doesn't. And these cases are not paid sufficient amount of attention to. Even what I'm doing now, see, for a mathematician, it's not terribly important to know how a mathematical model of a situation is built. I build it, and then I use my theory to compute. If I'm interested in beliefs, I'm interested in seeing how my beliefs change when my knowledge changes. And my knowledge may contain defaults. It may introduce new notions and so on. Okay? So it's important for me, since I'm interested in beliefs, to be able to reason about it. For frequentist view, it's irrelevant. So they don't study it. If I go to classical probability theorists and explain what I'm doing, I tried it a couple of times. One guy was fascinated and two couldn't figure out what I'm talking about. And there's some differences. Does it answer your question, at least a little bit?
Yes, thank you.
Okay, any other questions? Anybody else? I should probably, I'll probably just do one comment, Michael. You said that when you studied this in response to Vladimir's question, I had to study probability and measure theory many years after you. Still, the same sort of confusion
Ways
prevails.
too.
Yes, yeah.
And I'm sorry.
This same, it takes time. I mean, we are introduced to both, and then we are taught examples of where one or the other, like, where the frequentist approach may not work just as well.
Okay. By the way, I said, if you have any questions, of course I meant, and comments.
Anybody else with any questions or comments for Michael?
Well, thank you very much then.
Yes.
If you have any questions or comments, please write to me.
Yes, and just to make this clear, I have the recording of the talk. I'll stop in a minute, but then I plan to post it to the same mailing list where I posted the announcement of the talk. But if you want a recording and you were not on one of those lists, as in you got it from a friend or colleague, just send me an email and I can share the link with you. Okay. I think with that, I will thank Michael once again for making time and agreeing to do this talk on my request. This was a good way to get a sort of overview of logic and computer science on this World Logic Day. So I'm just going to end this with some applause for Michael. Okay. Thank you. I'm going to end this thing now. You all have a, I mean, if you're in the US, have a pleasant day. The rest of you, if you're in Europe, have a good evening and stay safe. Thank you. Bye.
Bye-bye.